And here we are at Superstellar Friday, which happens the first Friday of every month, except this month.
Because it was 4th of July.
It was the 4th of July, yes, it was. And so we're doing it on the 2nd. But the good news is, we have the Ask the Astronomer is here. And we have at least 8 telescopes, if not more than 1 telescope, for when it gets dark, to look at whatever might be visible. I think the moon should be up. Then at about 10 minutes to 12 minutes after we're finished with this presentation, we'll have a little break. You can use the restroom, get a drink, walk around, and we'll have a planetarium theater show about what's going on in the night sky. And I will be hosting that. And you can be thinking about if there's anything that you would like to learn about. Because I try to keep things informal and interactive, so I kind of let the audience guide the show. But have no fear, I could talk for hours. You don't have anything to say. There's that. So it's kind of like a triple header. You have a special presentation to try and introduce in just moments. And then we have the planetarium show, and we have telescopes outside if it's clearish, which I think is going to be clearish, and you have the New Hampshire Astronomical Society with their Ask the Astronomer. So if you have any questions about telescopes or any astronomy questions, we have people here to answer your questions. And we do this every first Friday night of every month, except this one. And it's obviously a different program. Any questions? All righty. Well, let me introduce you my left-hand man. This is Matt. And now let me introduce you our program. So these folks, we have Kevin, and we have Chris, and we have Matilda. Oh, Rachel. Rachel, right? Yeah. Well, it may not be Rachel, right? But it's great. And Matilda and Emily. It's with me.
Elmora.
Oh, I was gonna say that next. Oh, no. And then our king, and he's Dutch, so am I, so we're like best buddies. He's a sophomore, but he doesn't know what it means. And then we have Alex. And Alex is the same. And they're all from Hanover High School. They're high altitude balloon engineers. So you're gonna hear and learn about what do high altitude balloon engineers do at the high school level, which I think is really, awesome. The sooner you get involved in stuff, an important thing I think about high school in general is to start to figure out what you want to do and to try as many things as you can, because you don't want to think, I want to do that, and then you spend thousands and thousands of dollars and end up with, I don't want to do that. So, you know what I'm saying? All right. So, without any further ado, Kevin is in charge of the group, is the teacher. He teaches chemistry and STEM stuff at Lebanon High School. And
They're in trouble now.
oh, you just had that conversation. See, now she's remembering your name.
Yeah, all right.
It's just Abby's point of reporting.
Turn it over, and it's on the board, but I didn't want to turn around and look. So, yeah, no, sorry. I did that on purpose. Okay, so, Kevin, take it away.
Wish I met Dave years ago. I would have figured out what I wanted to do. I'm still figuring it out. Like I said, I'm 5, pretty much. I play a lot. I think that's what you should do, correctly. But keep that sense of curiosity.
Yep.
And so with that in mind, just think about this question for our presentation. You said anything from your space, what would you say? And so, we're a young balloon team. We started 2 years ago. And, I do not have a background in how to do ballooning, nor had I ever put it on my list that I want to learn how to do ballooning. But that's where it started. An opportunity came my way. And so one of the things I want you to think about, and it's what got me into it, is when's the next solar eclipse? And if you start to think out, we just have it, right? They occur all the time, sure, but not here. And so the next one around here is 2044. It's 20 years from now, just about. Which means I'll be 78. I'm not sure I'm still gonna be launching my own balloons then. And also, you think the last 40 years, like, where will you be when that happens? And what they're gonna be like? And so that brought us to such a special time last year. In 23 and 24, within a period of 7 months, we had 2 eclipses happen across the US, where most of us would get see the eclipse. And so we had the annual eclipse, that is this one, and we had the total eclipse, which is right here. You see, this would be the sweet spot of me, but everybody was going their sweet, you know. We'll think more about that tonight. I'm hoping, show of hands, how many of you got out to see the total eclipse? I know my audience, so I was counting on that. And when it happened, what things did you notice? What, dark? You get dark and temperature change, yeah. What about sounds? Yeah,
Yeah, the sun actually blocked it, so we had to wear the special glasses.
that's right, so you didn't get into your eye.
Yeah.
Excellent. Yeah, anybody hear night insects come out? Birds go to sleep. Okay, so all these different things happen. And the reason we got involved is, well, it was a really special time that eclipses were happening in the US. And so NASA put out this call, like, we want to get society and citizens involved in eclipse. And they started a program where they selected 53 schools, and there were only 5 high schools, and we were the only high school on the East Coast, so the public high school was selected to pull and play with everybody else. And they said, this is what we want you to do. We want you to launch IL-3 balloons. We want you to collect information on gravity waves, which I've never heard of gravity waves. That's a gravity wave right there. You see them all the time. It's temperature changes in the upper atmosphere, and the condensed clouds fill in the troughs of the waves. And our teammate, Avi Patel, actually captured this photo when we were in Oregon during that eclipse, January. Someone hands off to Hanover.
So our balloon is set up with the latex balloon at the top. There's a parachute here, and then we have our satellite tracking devices. Any data payloads that we want, so collecting information on like gravity waves, and then like a camera at the bottom. Depending on the launch, we might put in different sensors, like depending on what. So we don't just buy our sensors off the shelf. We often are given directions, a list of parts, and then we have to assemble them ourselves, which involves like soldering and testing. And we'll often encounter problems that we don't really know the answers to, so we'll be waiting for several days just for the manufacturers or other balloon teams who might know the answers. So building like the parts takes up most of our time and is very labor and time intensive. And then to actually protect the devices, we have these polystyrene boxes that when we started, we would just glue them together. But it would take just several days to make these boxes because you have to glue them. And then we also have to drill holes in the corners here so we can run the strings through. And all in all, it's just like taking a very long time. We tried these like laser cutting the polystyrene to save us time and sawing it and using these finger joints to put them together. So we wouldn't like as much time gluing, but it still took a long time filling the holes, and we still did have to wait for it to dry. So our new design are PLA 3D printed corners. So the polystyrene sheets will actually slide into these, so we don't have to use glue. And they have like holes in the here, that we can run the sprinklers at the same time, like probably 45 minutes it takes to fill the boxes. And so they save us a lot of time, and we launched probably I think 2 or 3 launches with them, and they've held up well, and we haven't seen any problems with them. And then our camera system is at the bottom of our balloon. We have 2 different camera systems. We have the GoPros here, which are like 8-band cameras that have 180 position, and then our Insta360 camera, and we can also put the GoPros on, but we don't usually mask. And then there's this cage here to protect the camera since it is at the bottom of the balloon. We don't want it breaking. So when it hits the ground, it actually slides up into the cover. So this 3D printed cover actually takes the impact. So how do you track a file to the whip? We use satellite tracking and communication. So if we use our balloon, that is like days and sometimes months of building and just like time in the workshop lost. And then also all of our data from the launch will be gone. So it's really important that we have these redundancies when we launch our balloons. We actually have 3 satellite tracking devices, and then we also have a air tag that we put in it so we can get a close range hopefully. And then while we're watching the launch, we actually can see it in real time because of an app we have on our phone. So we can see like the exact altitude of our balloon and its coordinates throughout the launch. So we can see when it pops. Oftentimes, we know, like we can start our retrieval early because we already know that it's popped. And we can save us time and drive out and leave it like around the time that it is.
One of the things that they dusted off in the 2017 Eclipse was this old vent. And the idea of the vent is, especially for an engineering team, you want to keep your balloon at maximum altitude and keep it there as long as possible. And so they were working on trying to figure out how to vent out the helium from the balloon when it reached 90,000 feet. So we can actually talk to it through the satellites as well. We sent it an email. When he said it open, close, and idle, that's about all we can do to the balloon. And like I said, this was from 2017. Didn't really work. We got it, we tried it, it leaked a lot, we couldn't control it. So we threw it out. And we said, well, we can do this. And we started engineering. This is what we came up with for the 2023 and 2024 Eclipse. And it worked really well. We have a motorized solenoid. It would open up just like a push rod in a car. And so we could send the signal open. It would open up. We could control the helium coming out. And like Matilda indicated, we would watch this graph and we discovered if we get to around 60,000 feet, we'd start pumping the brakes. We let out a little bit. And that's one of the frustrating things when you can't see it real time. So we wait for the graph and we wait for the acceleration to start slowing down. And if that doesn't work, we pump the brakes a little bit more. And hopefully we get to 90,000 feet and you understand why shortly 90,000 feet is a sweet spot for us, but we get there. So we had a lot of success with it. And we really liked this vent, but we felt like, you know, once you build something, you've always got more ideas. And so we had some more ideas. So we threw that out and we're now down to this vent right here that is just about finished. And the idea here is that we can put all of our components inside. We're calling it like bento boxes, like the Japanese bento boxes for lunch. And then we can just screw on other instruments down below that flex them. And actually, I need to also be honest that we just got rid of this one. We have a brand new design that we're testing next month too. So, you know, just, it's one of the things about the engineering. It keeps pushing us forward and seeing where that's going to go.
Okay, which do you think is higher, the summit of Mount Everest or where are the
Everest.
Everest? That is not that correct. Summit of Mount Everest is a little under 30,000 feet, whereas our balloon flies more than triple that, 90,000. More specifically, there are 3 layers to the Earth's atmosphere. The thermosphere is where the International Space Station is, and the troposphere is where any plane you've been on has flown. And we fly in between there, right in the stratosphere, to collect our data. Yeah. Let me just mention one thing about the video you're about to see. In preparation for the total solar eclipse in April, we did a number of practice launches so we could like hone out any mistakes and get it perfect. So the launch on the day of the eclipse will go off without any bumps. And this is a video from our first successful flight. And as you can see, we have the balloon, and strung under the balloon is a parachute and follows our payload to flight the data. This is an altitude chart of our first successful flight, September of 2023. This is Mount Washington over here, the little speck, and this is the height our balloon reaches. So as you can see, quite a lot higher than Mount Washington. And before launching our balloon, we use prediction software to figure out where we launch our balloon at a specific point, where it can land. In order to ensure, or at least attempt to ensure that it doesn't land in a body of water on the top of a mountain or in a city. But being in New Hampshire, the only other real option other than that is in a tree, which has happened like almost every single launch. So what are the possible ways to recover a payload? You could climb the tree, you could shake the tree, you could cut the tree down, and our newest solution, which is a slingshot, which launches a rope with a weight on the end over our payload in the tree, so you can yank it down. All of these practice launches culminated in our biggest practice launch in Bend, Oregon, for the annular solar eclipse. This occurred on October 14th, 2023. All of the balloon teams came together along that line of the eclipse in order to have, we call it like a dress rehearsal for the solar eclipse, because we all had to launch our balloons at a specific time to get them to reach 90,000 when totality occurred. There's just a photo of us watching the eclipse there, and it was really amazing to ensure that everything went out without a hitch. Going back to the height, what do you think happens when the balloon reaches 90,000 feet?
On its helium, it might just sit there, because helium is just flowing, it's less than, yes, you're down here. But as soon as the atmosphere, will see density as the helium inside the balloon and the balloon combined,
It could do that. It also expands so much that it can pop, which is what happens quite often. We also have a cut down enabled on our vent, so we can send signals to our vent and allow to cut a string that unravels around the balloon and release it. But in Oregon, so many balloons were up in the air at the time, the signals were crossed, and we weren't able to cut it down, so it ended up popping here. Now, all of these practice launches culminated in the total solar eclipse on April 4th, 2024. We traveled to Browser Point in New York to launch our balloon. Here you can see Bailey's beads, their phenomenon when the moon is crossing in front of the sun. The very left part of the sun show shines through the valleys in the moon, the craters, which is really interesting to see because the pictures capture it. So this is our flight path in the eclipse. It went off amazingly. We launched here, traveled across Vermont, and popped right here, and then came down there. These are all of the balloons from the Nationwide Eclipse Balloon Project teams across the United States. You see, we're right at the top. We got our balloons out, and we have data here from velocity, ground speed, and altitude. All of this data from the numerous eclipse ballooning teams came together to be published in a number of papers, as well as being included in a forthcoming book, The Eclipse Effect, that in December. And now this will talk about it.
So after we were done with the eclipses, we pivoted to observe a solar phenomenon called coronal mass ejections. Coronal mass ejections are really interesting. So the sun is a very dynamic body. The sun's magnetic field, what it does is that it twists, it will fold, and sometimes there's a knot of sorts of a lot of energy buildup, and the sun will release all that energy in the form of either a solar flare or a coronal mass ejection. Think of it as the sun is building up a lot of gas inside and it burns out. The difference between a coronal mass ejection and a solar flare is that solar flares are a lot more energetic and they move a lot faster. Whereas a solar flare might take about 10 or so minutes to come all the way to Earth, coronal mass ejections take about 10 hours at the minimum. 2025 was a very, very crucial year for us to observe the sun. Why? Well, the sun has cycles in its activity. Some years the sun is really active, some years the sun isn't so active. So I've got a little trivia question for you. How often does a solar maximum when the sun is really active occur? Anybody want to take a guess?
11 years.
11 years, bingo. And so this 11-year cycle is really, really critical to a lot of conditions in our atmosphere. For example, the activity of the sun is tied to Earth's temperature. For example, in the 1650s, during the Maunder minimum, when there were little to no sunspots or coronal mass ejections observed, the Earth's temperature did dip a little bit. Now, this isn't the only factor that contributes to Earth's temperature, but it is something very, very important because all creatures on Earth actually need a little bit of radiation from the sun to survive. We can't just be completely shielded from this radiation. 2025 was right at the peak of a solar cycle, which is really nice for us. Currently, because we're in July, we are well past that peak already. So we had to take advantage of all the time that we could this past spring to measure these coronal mass ejections. And Martine will talk a little bit about what we do.
So, why do you think scientists study cosmic rays from high altitudes rather than just from the ground? Yes, that's very close. Well, there are two main reasons. The first reason is that we don't want to measure from just the Earth, these background radiation, which can mess with the data and give us inaccurate results. And the second reason is because we want to fly high enough that we can be inside the optimal maximum, which is when we can detect muons and detect the most cosmic rays. Now, a 2014 study went to many regions of the world, and what they found is that in different longitudes, the higher longitude, the more radiation reaches Earth. And this is because the Earth's magnetic field acts as a shield, and it reflects cosmic rays away. However, at the poles, it lets more cosmic rays into Earth. Now, when a coronal mass ejection occurs, there might be a formation increase, which is when the coronal mass ejection acts as wind and blows dust particles, the cosmic rays, away from the Earth, leaving there a 5-day decrease in radiation. It just blasts all of the cosmic rays away from the Earth. And now, Alex.
So how do you detect radiation and what does the data look like? Well, we use 3 different radiation sensors to detect radiation, and the sensors use 2 different actual methods, one being a Geiger tube and one being a scintillator. The important difference between the 2 methods is that a Geiger tube detects general radiation, whereas a scintillator, especially in the case of the cosmic watch, can be used to detect a very specific amount of radiation. So the cosmic watch is very good at detecting muons, which are particles that occur through the degradation of cosmic rays as they interact with the atmosphere. Whereas the GMC 500 uses a Geiger counter, which is, at least for the GMC 500, noisier in the data and collects more general data. Now, this is the general type that you're expected to get from a balloon launch. It's taken from an old paper. And as you can see, as the balloon rises in the atmosphere, the effect of cosmic rays increases because the lower down you are, less rays reach you. That reaches a point called the Foster maximum, where the amount of radiation is at a peak. When you get above this layer of the atmosphere, the amount of radiation you're reading actually decreases. When the balloon pops, it falls back through the atmosphere and back through this layer of maximum radiation. So the radiation actually increases back up for a moment before falling all the way back down. This is data from our flight, and it closely matches the data that we're supposed to get if you ignore the horizontal stretching and squishing. This is from two GMC 500s flowing in tandem, and you can see that data is a bit noisy at the top, but it does follow general path. And this is another visualization of the flight path of the balloon, and you can really compare its height with Mount Washington and also with the curvature of the Earth. It gives you another perspective about how tall the balloon actually, or how high the balloon actually gets. This is data from the radio code, which is using a scintillator, and it's more accurate, and you can actually see very small nuances in the balloon's path. For example, this initial flat point is when the balloon is laying on the ground before launch. When the balloon launches, the effect of background radiation from the Earth decreases, so the amount of radiation actually decreases. But as it rises up to the Foster maximum, radiation count increases, decreases as it gets above that band. When it pops, there's this large spike. It's actually just a issue with the sensor, not indicative of more radiation from the balloon popping. And as it falls through the atmosphere, the amount of radiation readings increase, and then decreases back. And then when it hits the Earth background radiation brings it back up to the baseline level.
No, when we saw that spike here, we were pretty excited. We thought we discovered something new. I thought we were gonna give it the new name, but it wasn't true. So we're still looking for that. Now, as we finish up with the solar eclipse stuff and with the CMEs, our team is beginning to pivot. And it's a real dynamic time right now in science. And so we're starting to think about what can we do next. We've got 2 years under our belt. We know how to launch things. We can get things to 90,000 feet. We can collect data. And so now we're going to show these over our future projects.
All right, so in terms of some of our future projects, we will be integrating radiation biology into our research in order to fully take advantage of the high levels of radiation we can expose biological samples to. Because the data that we can acquire from this might be indicative of the biological impact of spaceflight. So in terms of the samples we'll be using, we will be using extremophiles, which refers to the microorganisms that can survive very extreme environments, such as salt lakes, like the one shown here. And the one shown here is a salt lake off the coast of Western Australia, and it's pink because of red carotenoid pigments of palobacteria, which is what we'll be using for arsenic. So this is an image of some of the samples we've already taken up. And in terms of samples we can use, there are some species of palobacteria that grow in Antarctica, and we saw that we thought, well, it would be nice if we could get our hands on bacteria from Antarctica. But fortunately for us, past studies actually shown that the more available species can survive very well in stratospheric conditions. Something that past studies also showed us and sort of warned us about, you can see in this image. So can you see anything different between this bacteria and what's shown here? Well, one of them is pink and the other one's white. And that actually has to do with exposure to radiation, which changes phenotypic expression for about 2 generations. And then when it comes back to Earth, it'll go pink again. All right, so it's really nice that palobacteria can survive stratospheric conditions, but you might hear that and be thinking, why even send it up again if you've already gotten results from 2017? Well, we have a pretty rare and special opportunity to expose samples to high levels of radiation, like what they were talking about, whether it be from CMEs or solar maximums, or the solar maximum, which can show us a little bit about the biological impact of spaceflight or just high radiation environments in general. So we'll be analyzing the results in 3 main ways. One is spectrophotometric data. We'll be using a spectrometer to look at the absorbance profile of palobacteria. As you can see here, that usually has 3 pretty distinct peaks from proteins that palobacteria DNA codes for, and any change in that profile can show us mutations that occur and change the DNA. We'll also be looking at DNA byproducts, and for palobacteria in particular, often radiation-induced mutation we'll change the bacteria so that certain genes aren't coded for and they aren't as resistant in UV radiation. So we'll be using gel electrophoresis to give some information about whether those mutations occur. And then finally, we'll actually just look at the survival rate of bacteria by stripping them onto plates and seeing how many polychlorinated units there's.
Thank you. If anything, that is one of my favorite tips, because you would not believe what we've gone through with cameras to try to capture images. During the eclipse, you tried streaming data, but you saw the noise. There was so much traffic up there that we had a lot of trouble streaming data. We did get it on film, but it was really kind of grainy. And so we went back to the drawing board. It's like, well, everyone else is getting great film. Why can't we? And so this was our first success getting really good film from the GoPro cameras. And we've since had success with the Insta360. But I mean, just, you see that little bit there? That's the only reason that you can breathe. I mean, it's so thin to be able to put that in perspective and see it. There's the curvature of the planet, there's nothing, and that's it, right? And so when I show people, that's the first photo, I got it in my phone, I show everybody. What do you do? I fly high altitude. And they're the ones who can talk about it. I mean, they're doing the work. I'm just along for the ride. This is our Insta360. You can see here, we've got a little bit of some scratches, which we're working on, take care of. But one of my goals is how can we improve the video? And everyone's moving to VR. And so we're experimenting with the Apple Vision Pro headset that you can put on, so that you'll be able to be right in that environment. And this summer, we hope to capture a sunrise launch, which means we'll get at 4 a.m., get our balloon off the ground, and capture the sun coming over, and then watch it in total VR. So that's my goal. That's what I want to do. It should be a good time. We're also collaborating. There was this, we have an Instagram page, and we attract all types who are interested in Eclipse. And I started following, I also do woodworking at school. I teach chemistry, I teach engineering, I teach woodworking. And this woodworker had a site, and he's been trying to get this UFO onto a SpaceX rocket. And 310 days. And then he tried any rocket. Now we're up to 330. And finally I said, look, I can't get it on a rocket, but I can send it up on a high altitude balloon. And instantly Jake and I started talking. We've done North Carolina. He said, great. He sent it up. So we had to redesign our whole rig so we could come up with these platforms. And so I crazy glued his UFO because I didn't want to lose it on him. And we sent it up, and we've got this photo. And we've got another one too, where he developed, you can see the curvature and everything else. And so Jake was pretty excited, and it's now home on his collection. So he's going for another goal now, getting one in a movie, but I can't help him with that. We're also want to start encouraging more people to get involved. As we're doing outreach with schools around us, we've asked people in the high school to come play. We've got several of the students who are coming down to do things, but we're getting into cubes in space. And so these are actual experiments that students designed. When I did a test run with my engineering class, NASA runs this, and they set it up on a sounding rocket. But the sounding rocket just goes a little bit higher than us. It goes about 130,000 feet, which we're going to hit this summer. I've got plans. But we can hit that. And so students design their experiment, they test it on the ground, they have engineering constrictions. These are actually about half the size of this. So very small cubes, your whole experiment has to fit in there. This one is yeast being exposed. We 3D printed some carabiners. You know those little packets of drying beads that you get in all your Amazon packages? Well, it turns out that there may be a way to extract the water from that. That'd be great for long space flights, especially if you have to keep yourself more moisture-free on a long space flight. And so we've got several experiments. They all got accepted, and they went up on a sounding rocket. So we're like, well, we could do that. So we're going to offer it to our middle school science teachers, even elementary. We would show up, we would help the kids understand the experiment, give them a set of prototype. We will fly it for you. Come on launch day and launch it with us. We'll go get it. I'm not taking a bunch of elementary school kids out to the woods. Exciting, but no. And then, give the kids back to the experiment and see what happened. We have Theo, who's a friend of the balloon group, who's actually growing these up some sunflower seeds with Theo. And so he's got sunflower seeds that right here, and sometimes we send out, they get exposed to radiation. We'll find out what happens to Theo's sunflower seeds. But really, at this point, it's like, what can we do And there's everything we can do. And it's just to get people encouraged into thinking about altitude, science, and just go do something. It's possible. You know, it's not wait for the experts, wait to get your PhD, do it now. And so if you could send anything in your space, one, we can do that for you. And two, what do you want to send? That's the question I'd like to leave you with. But I think we can pull it off. There's a website that you can check us out. This is everyone who's been part of the team, the current makeup of the team. It'll grow again this fall. We will be looking for 5 more people to join us. And thank everybody. It's not just us. We have a lot of partners that contribute to this. Because one tank of helium costs about $1,000, and to fly one balloon, it is 2 tanks of helium. Wow. And so we're $2,000 a flight, and that doesn't count our instruments and everything else in the hours we put in. And it's all volunteer, which is awesome. You know, for them to come down and spend the time to do this, it's just fabulous. So if you want to come out and play, we're looking for players. At this point, thank you. And any questions? Questions for them or me or?
One thing which goes to space and radiation and comes back for it, does it still have some of that radiation remaining on it, or is it come off, is it cut back?
Hold on.
It's like, it's going to the dentist.
I don't think so.
It's like high energy particles, they're going right through everything.
Yeah.
And so while it's 10 times the amount,
Yeah.
it's, like the dentist turned on the X-ray too long.
You gotta hit the projector button twice to turn it off.
Sure.
It showed, in New York or where was it?
Rouse's Point, yeah.
Yeah. So where is,
So we launched from Rouse's Point. This is about having this month, I believe, where it popped. And several of us spent a long time in cars trying to get, because as many of you know, there are a lot of people who came up with a total eclipse. And we left New York and we're about a half hour ahead of them until we got here. And then we spent the next 7 hours to get over to Littleton, New Hampshire, where a balloon came down. We actually had 2 of them. You don't see the second one in the slide. One of them was the NASA payload, and the other one was a separate balloon, just our payload. We sent up separate instruments. It turns out that balloons can only be a certain weight. And I love this term. You can have up to 12 pounds, because that's considered digestible by airplane engines. After 12 pounds, you can't do that. So yeah, we hit this wall.
is that Lake Champlain?
That is Lake Champlain, yeah. And so we can, in our current balloon, we usually come in just around 11.5. We'll launch that one. That's our big balloon that'll take 2 tanks of helium. And then we have a lighter one that's usually about 6 pounds. That's 1 tank, the smaller balloon. This summer, we're gonna launch a really big balloon with a really light payload that we're down to 3.5. But normally we hit about 90. I think we'll be able to hit 130,000. That's our goal.
Now the 12 pound, which is the balloon and
Everything.
payload, everything.
Box, balloon, string, payload, batteries. You know, so 1 lithium battery for our instrument. I mean, you know, like the camera battery, our camera is so heavy that we will make trade-offs. Try to manage the weight. Spend a lot of time doing the weight. You know, it's interesting engineering criteria, right?
So that solid length there, is that the Canadian border?
Yes.
And where's Burlington, Vermont?
Burlington this is right here, that's St. Albans, so this is Burlington here. This is the islands. So St. Albans, Swanton, the Greens. And then you get to the border in New Hampshire. And so we ended up here where one guy was really nice, let us cut down one of the small maple trees that were down. And the other one was on a tree, we couldn't find the owners, we think they were in Florida, so we kept going back. And by luck, we had a really good high windstorm, and next time, I think the 3rd or 4th time we went back, it was on the ground. So we recovered it. But you know, we've had some pretty good luck, we've missed power lines, we've missed the lake, but we've had teams, there's still 20 teams playing the CMEs, and a couple teams had their stuff go to the ocean. That sucks. Nothing survives the water. It's not watertight. Yeah.
I have a couple of questions
Sure.
regarding solar eclipse. One is, are you able to pivot camera, because the thing is going up, it's spinning, we can see on one of the videos, but are you able to aim it to where the solar eclipse is happening? And my second question is, what could you see at that altitude about the solar eclipse that we couldn't see on Earth?
First question. Can you control it? What you can't see in this video is the Insta360 software. When you use that software on a computer, you can actually pan around and stop the motion of it
Oh, wow.
with the software. There is a team at Huntsville, Alabama, that has designed and uses a nitrogen tank. It actually gets squirts out, and it's using the accelerometer from a phone. And so it's squirting out a little bit of gas and trying to slow it down. They've slowed it down, but haven't stopped it. But still, that's great for a team that's 3D printing, just like us, testing, breaking things. The second thing is that, what could we see up there? It was more about the data collection for the eclipse that NASA wanted, which is all about the gravity waves, temperature.
You're talking about the
video-
radiation from the sun and how it must have diminished then and things like that.
For the eclipse, we didn't care.
Oh,
That part wasn't part of the experiment. For them, they just wanted to know about the temperature differences.
okay.
But the streaming was something no one had done. And that's why they put the challenge out to all 53 teams. Could you actually stream this event so we could share it with people during the actual event? And they came up with some ingenious ways to share it. One of the ways that we also had an instrument out there called a soundscape, and it was recording the sound of the insects and when they disappeared. And they were trying to understand the biology of what happened during an eclipse. The other thing they had is we had a second instrument that as the sun diminished and it got darker, it would play different frequencies. So people who were blind could enjoy the eclipse as well from our balloons being up there. Streaming was a real interesting problem because with satellite data, it's like I mentioned, it's an email. And so it's very small bandwidth. And so we had 53 balloons up there. We intended on floating our balloon and keep it up there, but we couldn't talk to it. Normally, when we send it an email, it takes 9 seconds to hit the balloon and come back. It took 45 minutes because there was so much traffic in the air and everyone on their cell phone sharing all their wonderful pictures, shut down the cell network, and we couldn't talk to the balloon. So it was a really big experiment. Could you do this on a large scale and get everyone to enjoy it? So the camera was bonus. We spent a lot of time with that camera. We've since tossed that one out, and now we're working with Instas and GoPros. The Raspberry Pi was just difficult to work with. Other questions? Yeah.
Yeah, one of you mentioned at the very start the use of polystyrene specifically for a portion of the payload, or maybe it was part of the balloon itself. Was there a specific reason that you chose polystyrene over other compounds? Is it better at shielding from high energy radiation, or was that just kind of a material that's been used a lot in the past?
There is like, versatile material that we already like you should have in the shop. I don't really think that there has been some research on like blocking radiation, but normally that's like something you'll put on a wrap around the box. But we didn't really consider radiation when we were choosing polystyrene.
All right.
I'd also like to say that blocking radiation would be very hard. You have to have like layers of lead or other materials, and with the 12-pound weight limit and also with the cost of helium, it would be prohibitive to do so. And so we weren't really worried about radiation affecting the payload.
And the other thing's temperature. It goes through temperature extremes. It gets really cold. We've documented that it's about -75. The other problem that we have up there is that there are so few air molecules, things overheat. You have things getting really cold, and then when they reach their maximum altitude, they start heating up. The problem we have with the cameras is our Insta keeps shutting down. It's a thermal problem that heats up too much on us. We were flying in a protective case, plastic case. Now we just fly it exposed. We take the chance of ruining it, but it's the only way we can keep it cool enough. We've got a couple other ideas that we're working on. Like you could put a small aluminum block, seal away the heat, but then we start coming up against weight problems. So it's great engineering, right? We're designing stuff that's going to be used other places, and maybe for the next eclipse.
Yeah.
I'll be able to go to launch.
Who funds your project?
Everybody. Yeah, it really comes from the New Hampshire Space Grant Consortium.
Yeah.
It comes from the Montana Space Grant Consortium. That was the largest one. They worked directly with NASA. And they're the ones who came up with the idea like, oh, let's do citizen science. We've got an opportunity to eclipse happening. And their money just closed down June 30th. So hopefully they scrape together another budget for movie flying. But at this point, we started looking for, if you know anybody, we're looking for people interested in contributing to keep us flying. But I keep writing grants and get lucky with grants and we're kind of scrapping it together.
Question about the bacteria. You plan to have a control.
Yeah, we're growing bacteria on Earth as well. We plan to, we're playing around with whether we grow it at room temperature or in the fridge or in the freezer to sort of limit that variable. But it doesn't really change the growth rate, the temperature, because it's so, like, it's such an extreme file, so.
We've thought about contacting a dentist, because they've got an x-ray machine, we can expose it to a certain amount of x-rays. And that way we can say, look, if you got exposed to this much here, how does it compare to ours? Everyone's done it, so everything's on the table. I look forward to what it gets them up with. I just help, I just point in directions. Yeah.
Yeah, this may be a bit more of a history question as opposed to the science bit, but I believe you mentioned the Maunder minimum, or however you say that. Maunder, yeah. Was that due to a lack of observation of the sun itself, or was the sun in a particularly inactive point in its history during that time?
I actually don't fully know the answer to that. There are the earliest like sunspot observations were around early 1600s-ish. So we had as humanity had observed sunspots before. I mean, they were a known phenomena. There are also like much smaller instances of maxima being lower. For example, the Dalton minimum, it was around, I think, 1880-ish. And the thing with those up and down cycles is that sometimes cycles are higher than others. So like, for example, this past cycle was a lot higher than the one in 2014, hence why there was this effort to try to capture data from this cycle. But yeah, I think it is definitely something interesting to look at the way that the sun's radiation affects Earth's temperature.
What it comes down to is it was a lot less sunspots. And we didn't have the satellites, then to study it. But it's an interesting correlation because with the lack of sunspots, you also see a small ice age. It's fascinating in terms of weather.
I was about to say, sorry, it was a real fact.
Yeah, and the other thing that pilots are interested in, and I know I got a pilot here, is that being up in the air, they get exposed to more radiation. So the other part of this experiment that they were looking at is how much radiation, what are the effects of that, and sunspot activity. Plus, you had all these teams. I mean, the other advantage is you had, once again, for the Eclipse, there were 53 teams, 750 individuals that you just trained on how to fly altitude balloons, and to just say, okay, we're done. And so luckily this was occurring a year later. They ended up only picking 20 teams, and there were only 2 high schools. We were only in public high school that got picked. But we got to play for the rest of the year trying to collect that data and show what we get done. Well, Alex mentioned the 3 sensors. No one had flown those before. It was us saying, what could be done and how can we do it? And so teams are flying on every direction. They're putting in next to radioisotopes in the lab. The cosmic watch had to be soldered together. And so Tehan, who's not here, had the smallest parts ever. And he liked working in the dark soldering. And I don't know how he did it, but he made us 3 working units. So it came from MIT. They're like, this is great, but you got to build it. And so we're like, okay, we'll build it. We'll figure it out. And so it was fun. We did. And even published in a simulator that it's this, the simulator is a piece of plastic. It has 2 proteins in it. One of them will fluoresce, but it only, that fluorescent light only travels like 2 millimeters. So you need the second compound that gets activated and it can travel farther. And basically it gets picked up by a light sensor. But the plastic is just molded, so it comes cloudy. And Eleonora and Gus spent 6 or 7 hours sanding it down to 6,000 grit and couldn't get it. And we needed it crystal clear. And so we just kept sanding, we couldn't get it. And someone had read, well, we heated a little bit. So we're like, oh, we can't do it anyway. So we got a heat gun, we heated it. and it looked like a Zamboni hitting ice. It just instantly smoothed out. And when you hold it up to the light, instead of being frosty white, you can see that purple of fluorescent chemicals. Absolutely, it's one of those things I've seen out at night. It's absolutely gorgeous. And then we celebrated in that home this week. That's it, we're done. So lots of good stories come out of it. Yeah.
You have a weather specialist on your team? I mean, I imagine meteorology would be one of your key aspects of flying.
I've gotten really good at reading the prediction stuff. So we do have prediction software that's out there. It's good for about 7 days. But in terms of atmospheric ballooning, there are teams that do that. We don't. We focus more on the engineering side of it. Plymouth State has an atmospheric team, and they were also flying. They like to fly sound hubs, which are a device about this big, costs about $100, and they'll launch one every 10 minutes, sometimes every hour. There was one team during the Eclipse, and all it does is record data, pressure, humidity, temperature, and they were launching every half hour for 24 hours. They're much smaller balloons, so they're going right and left, but still an organizational nightmare just to be doing it all night long. And the sound hubs, they don't collect them. Sometimes they'll put a little tag on, says, hey, if you found this, we'll give you $10 to tell us and return it back to us. But they launch sound hubs all the time. NOAA does too, and lots of the weather stations fly sound hubs. But I'm a natural tinkerer, so engineering appeals to me.
Makes sense to me, you need to know what the weather pattern were to see where the way you launch it was gonna end up.
Yeah, I rely a lot upon the predicting software. And it's, like I said, it's really good. If you pay attention to it and dial in your weights. What we've started doing is we have a spreadsheet. Now we're up to 8 launches. And so as we get more launches, we're able to make much better predictions about where it's coming down.
Okay.
Yeah, I guess if you want to be our atmosphere guy, come on down. Always looking for more teammates.
About the poster, these three creative parts that you use to put the box together. How do they grab a hold of polystyrene so the box doesn't just slip apart again?
They are like really tightly fit so that you can just slip them in, and we also zip tie them together. So on the outside of these corners, we have a little, do you have an example?
I don't have one.
Okay, so we have two like kind of vertical channels on the outside. One is for the string that hooks it up to all the other payloads into the balloon. Then the other is just for a zip tie. So right before launch, you'll see us all frantically zip tying things together, and we gotta cut the zip ties nicely. So that's in our hole right there. That's for the guide string, and then the outer hole is for the zip tie. And so it just all slides in really nicely. And the nice thing about this is that it's really modular as well. So that if we need to use a thicker polystyrene, then we can do that as well. So we are about to begin an experiment about combining the thickness of polystyrene with insulating materials.
And this is, as you know, it's old now. We've got a new design. One of the problems is, Matilda mentioned, it takes 45 minutes to string all the payloads. And then let's say, oh, we didn't want to fly that instrument, or we've got a new idea, we'd have to unstring everything to get to that one. So we actually now have put a lip here, and we're using small carabiners, so we can flip them in and out of the guide string. So now we can make it much more modular. That's the plan anyway. It's version 5. Yeah.
What do you need to get a bottom of 1,000 feet?
Done to 3 pounds now,
Yeah, 3.5.
Yeah.
And we normally fly a 1,600 grand balloon. We're going about a 2,000 grand. Balloon prices change dramatically as you climb up. A 1,600 grand balloon is about $150. A 2,000 grand balloon is almost 350. And the really big one, which I hope we get to fly, is a 4,000 grand balloon that costs almost $1,000. Then the game you play, this is where the chemistry comes in, is that you just don't fill it and let it go. It's an expansion rate of the latex as it travels through the layers. So we actually underfill the balloons so you can play on that expansion rate to get to a higher rate. The record's 170. We can hit 130 and go for 170. I mean, you guys have been great, so you guys are awesome.
One more question.
Sure.
The coordinate with the FAA,
Yes,
your launches.
that is so scary. It's like going to the DMV, but on steroids. When I talked to them, I had to file this NOTAM, called a Notice to All Airmen. And so I called in about 24 hours before, and I let them know, where we're launching from, the closest airport is going. I think we've encountered one of our NOTAMs before. But yeah, we have to file a NOTAM with the FAA, and yeah, I'm getting better at it, they're getting to know me, but the first couple times it was so intense. And I'm sure I stuttered or something, because when he asked the name of the high school, I said, well, it's Hanover High School, and he heard Hanover. So we wanted to make t-shirts, Hanover High School, I don't believe it, but we resisted.
Have they ever been in trouble about that? Or just-
No, they're incredibly friendly. They ask questions about what we're doing. There are some changes coming down in light of the balloons that they shot down. It's taken some time now, and they're thinking about making us requiring us to fly just on glass, a special instrument that would put us on their radar, incredibly expensive. And so right now, there lots of teams are talking about it, and I think they're gonna hold off making us go to that extreme, but that's one of the things that they have thought about doing.
And that would add weight.
Yeah,
Yeah.
it's about, and it costs about $2,500 just for the sensor. And so, in terms of a balloon program like this and making it reachable for high school kids, when you start looking at how many high schools actually had the two balloons, you can count them on one hand. And it's such an amazing opportunity, because it's real science, especially in light of what's happening, global warming, bacterial stuff, temperatures, everything can be put into a paper and published, because we just got back from a meeting and there were an academic having to do a meeting, there were 46 people there. So it's like, yeah, you can make a real difference. I think that's where I want to go with it. So yeah, we launched. You're supposed to file, not everyone does. But most of the teams I work with do. The other thing is other teams are beginning to fly hydrogen instead of helium, cheaper. But I won't fly hydrogen. I saw the Hindenburg too many times. It's a lot cheaper than $30 a tank compared to 1,000. So, yeah, that'll be exciting too, right?
And it's like a lot, and it's, and he kind of sure.
There's a team out west who likes to fly theirs because they collect a lot of data during thunderstorms. They like to do lightning flights. I'm not into that. Here, hold the balloon. Well, thank you. There's some stuff, props that we brought out back. There's also stickers and patches. It's always nice to walk away with some free swag to put on your neighbor's house.
Thank you, Kevin and team. Let me try it. Chris, Eleanor, Hilda, Martine, Alex, Rachel. You want to look? So what we're gonna do now is click on the button, 8 o'clock. About 8:15, meet in the theater. So if you're familiar, you know the way. If you're not, you're just gonna go towards, there's a hallway that says planetarium, and it's that hallway, surprisingly enough. And you're gonna go down the hallway, and the door is down there, and about 8:15, I'll open the door and you come in and we'll have a good planetarium show about the United States. Sound good? So you can see if there's anything going on. If the moon's up, which it might be, they might be looking at it. I don't know if it's here or not. But you can talk to the people, the NASA, not NASA, Man's astronomical people, and walk around, get a drink. And at 8:15, we'll see you at the planetarium theater. Thank you.
Thank you.
All right. So